Hi everybody, this is Dr. Nigro with the second screencast for our unit on Newton's third law and momentum. All right, for this screencast, we're going to be looking at momentum, collisions, and then we're going to look specifically at the three different types of collisions. All right, so to start, I have two cars here. Well, I guess one's technically a truck. I have a smart car, and then I have an 18-wheel semi-truck. So the question is, which vehicle would you want to be driving during a crash? And most people will say they want to be in the truck if the two are going to collide. All right, which do you think would move farther after head-on collision? And this is a little bit tricky. I think the better question is the second one, is who gets pushed around. All right, and the car should be pushed by the truck because technically they're going to go the same distance once they collide. All right. Which vehicle will be harder to stop? And the answer there, I would go with truck. And so then the question is why? Why does the car get pushed around by the truck? And why is the truck harder to stop? And in class, what a lot of students said is the truck has more momentum. And that's a great word. More momentum. All right. I also had several students say the truck also has more mass. All right, which is true. Both of those are great ways to think about this particular example. All right. Momentum, though, is a good term for what we're going to be looking at when we talk about collisions. So that momentum of the object is really a measure of the force that that object possesses while it is in motion. All right. So when you talk about the momentum of something, you're really talking about how much speed is it carrying and how massive is the object. So when it comes to momentum, we use a capital P for our variable symbol. We're going to need to know the mass of the object and its velocity. And if we know these two variables, we're going to be able to calculate the momentum. Now, the unit here is a little messy. All right, we're going to have a kilogram because of that mass, and then we're going to multiply that by meters per second, right? And unfortunately, there's no good unit like a joule or a newton that represents this compound unit, so we just have to keep it in mind, all right? Now, when it comes to relationships between these variables, all right, you can see that the momentum will increase if the mass increases or the velocity increases. So we have direct relationships between mass and velocity and momentum. All right. Now let's look at collision specifically. So we'll start with the definition. What is a collision? And most people will say a collision is when two things run into each other. And that's exactly right. In physics, we call it a short duration event between two objects. All right. So when two objects collide, they bring their own momentum into that collision. So for an example, I was talking about two football players who collide on the field. All right. So if you have player A and player B running towards each other, they are going to run into each other unless one ducks out of the way. There are three real options for what can happen as part of this collision. All right. A could push B backwards. All right, another option would be B could push A backwards. And then the final option would be if A and B are both stopped. All right, so in other words, they both stop moving. All right, now which of these three situations we have depends on the mass of A and the velocity of A, and then the mass of B and the velocity of B. So the momentum of each of these players is going to influence what happens as part of that collision. All right. The key to any collision is that the total momentum before that collision must equal the total momentum after that collision. So whatever momentum is brought into a collision must also be present afterwards. So in other words, momentum is conserved. All right, so we tend to represent this by saying the momentum before that collision is going to be equal to the momentum after. All right, now what that looks like in terms of formulas depends on the type of collision. And there are three types of collisions. All right, we're going to start with a recoil collision. All right, so one of your jobs is going to be to recognize what type of collision is occurring based on the description of that collision. For recoil collisions, there are two key points you should look out for. One, both objects involved in that collision are not moving initially. All right. The second clue that we have a recoil collision is that the objects move in opposite directions after. All right, so initially no movement, and then afterwards they move away from each other. All right, so for an example, if you have ever watched figure skating in the Winter Olympics, in particular the pairs or the ice dancing competitions, there tend to be points during those routines where the two skaters are right next to each other and they push away from each other. All right, so that would be an example of a recoil collision. The word collision's a little misleading here because they don't really collide, they just push away from each other. All right, so let's look at an example. All right, so for this situation, I have two carts, cart A and cart B, and they're sitting on a frictionless track, motionless. Each cart has a mass of 1 kilogram. Suddenly, the two carts explode away from each other, moving in opposite directions with velocities of 2 meters per second each. All right, so fill in the following table and answer the questions. All right, so we're going to start with a diagram. So for this particular situation, I have cart A, and then I have cart B, and they are just sitting there doing nothing. All right, over on this portion of the table, I'm going to use it to calculate the momentum of A and the momentum of B, and then the total momentum before, and then we'll look at what happens after. So for momentum, I need to know the mass of A and the velocity of A. And for cart B, I need to know the mass of B and the velocity of B. So according to the problem, cart A is 1 kilogram, and it's initially motionless, so no velocity. Cart B is 1 kilogram, and it's initially motionless, so 0 velocity. I can multiply those two values together, and I find the momentum of A before is 0, and then for B, also 0. The total momentum is the momentum of object A plus the momentum of object B, and in this case, 0 plus 0 equals 0. Now, after the explosion, all right, so now I've got cart A, but it's moving in this direction at 2 meters per second. And at the same time, cart B is moving, but in the opposite direction at 2 meters per second. All right, now I'm going to designate right as positive and left as negative, and I need to use those signs when I list my velocity values, because remember, we have to include direction with those. All right, so again, we're going to look at the mass of A, the velocity of A. So we've got 1 kilogram, and we're a negative 2 meters per second for velocity, and I can multiply those to get my momentum, which will be a negative 2, and then kilograms times meters per second for my unit. I look at cart B, I've got the mass of B, the velocity of B, so 1 kilogram and then a positive 2 meters per second. And if I multiply those, I'll get my momentum, and that's going to be a 2 kilograms times meters per second value. All right? So just like before, the momentum of A plus the momentum of B will be the total momentum, and this time it's for after. So a negative 2 kilograms times meters per second plus a positive 2 kilograms times meters per second is 0. So as you can see, this is before, this is after, and they are equal, which means momentum has been conserved. All right, so we showed this, which now lets us kind of build a formula for recoil. All right, for this particular problem, we knew the momentum and velocity values for both carts before and after. So we were really just proving conservation of momentum. But a lot of these problems, you're going to know 3 of the 4 variables, and you're going to have to find the other ones. So having a formula is also useful. All right, so we know that the momentum before was 0, and then that was equal to the sum of the momentum of cart A and cart B after. All right, so for cart A, it was a negative mass of A, velocity of A, and then we added to that a positive mass of B and velocity of B. All right, if we move this to the other side of the equal sign, it will become positive, and we get our recoil formula, which is the mass of object A times its velocity has to be equal to the mass of object B times its velocity. Okay? All right, so I'm going to pause here, and I'm going to set up a third screencast where we'll look at elastic and inelastic, because those two types of collisions are pretty similar. All right? But for this one, this is our key takeaway for our recoil. Okay?